Hello, this is going to be a short video on the scientific method. Go ahead and share the screen. Again, these are notes from Moodle under lecture notes. And so it's just this one page with a couple pictures here at the end. So basically, I'm going to lay out why science is different than most other things. And the steps that one uses to perform science are called the scientific method. First, we'll just talk about the steps. We'll just name the steps. So step one is state the problem. Seems kind of obvious, but you need to decide what it is that you're trying to solve. The next thing you do is research and background on that. So stating the problem might take you a while to exactly figure out what it is that you're looking for. Sometimes it's really easy. Sometimes it's more difficult. But the research and background part, this is not what most people think about science, but this is where most of your time is spent. So you will read everything you possibly can about the topic, every work that everybody else has done to try to further the scientific knowledge. Your goal is to further science. So you learn everything that other people have learned, and then you go past that, and that's science. That's how the whole process works. There's a great quote in Jurassic Park talking about standing on the shoulders of giants and not taking responsibility for your actions. That can be a problem, but for the most part, what we're trying to do is learn everything that everybody else has done and then take the next step. The next thing, after you've spent probably years reading everything you can about the subject matter, you come up with a hypothesis about what you would expect to happen during an experiment. Then you would test the hypothesis. So this is actually the thing that most people think scientists are doing all the time, which is experimenting. It's usually not the case. There's more reading than there is experimentation. And then after the experiment is finished, then you draw conclusions from the data, and sometimes you have to reform your hypothesis and sometimes you don't, depends on what the situation is. So I'm going to use another example on how the scientific method works. And so I'm going to use baseball. So step one, problem. A pitcher needs to get a batter out. Okay, so pitcher standing up there needs to strike the guy out, or needs to get the guy to ground out, or just needs to get an out. So what does that pitcher do? Well, if you're a good pitcher, what you'll do is you'll research that batter. What is that batter's tendencies? Do they like to swing at the first pitch? Do they like to let the first pitch go by? Do they like curveballs? Do they like fastballs? Can they hit balls high? Can they hit balls low? Do they like an outside, inside? You'll learn exactly the tendencies that a particular batter is going to have. And then you will have a hypothesis. Your hypothesis is the pitcher, the catcher, and the pitching coach will decide, okay, we are going to pitch this one particular person in this particular fashion. So that's our hypothesis. Maybe first pitch is a ball. The next pitch is an inside strike. The next pitch is a curveball. So they'll go through all the processes of what they're going to do. All of this is set out beforehand. It's not like they're making this up as they go. The next is they're going to test the hypothesis. So that's they go ahead and the pitcher throws the pitches and we see what the result is. And after the pitcher is finished and they're in there on the next inning, or maybe after the game's over, they'll go back and say, okay, so we threw that guy a first pitch, low fastball, and he hit a home run. Let's not do that again. Or we got that guy out on 3 straight pitches. We want to approach that in the same fashion next time, something of that nature. So let me show you. So this guy's name is Greg Maddux. He was the best pitcher in the National League for 4 years. He won the Cy Young Award. He's 6 feet tall and 170 pounds. Usually Major League Baseball pitchers' fastballs are in the mid to high 90s, and Greg's fastball was about 89 miles an hour, which might not seem like a big deal, 6 to 11 miles an hour, but it's a huge deal. His fastball was considered to be slow. What Greg did have going for him is 2 things. One, he could put a pitch wherever he wanted it. So if he wanted it to be right at your knees, right at the edge of the plate on the outside, he could throw that ball. And the other thing he had going for him is he learned from his high school science teachers about the scientific method. He followed this process to the T. He would watch every single at bat against every batter that he was going to play in the next game, every single one of them, repeatedly. and you would know exactly what that person's tendencies were. When you stepped up to the plate against Greg, Greg knew what you were going to do before you knew what you were going to do. That's how well he watched you. So the counterpart to Greg Maddux is Tony Gwynn. Tony Gwynn is 5'11", 225 pounds. He himself would say he's a portly baseball player who plays first base so he doesn't have to run. He has one of the most prolific hit totals in all of baseball. And the reason that he did, even though that he's an overweight, short baseball player, is he also followed the scientific method. So some of the best games that I ever saw were when the Braves were playing the Padres and Greg was pitching against Tony. These at-bats would go on for a while. It was very scientific, for sure, as Greg knew what Tony wanted to do and Tony knew what Greg wanted to do. And so they would try to break their tendencies because they knew the other one was getting into their head. So there's baseball analogies for you. Now we're going to talk about these two guys. So in 1989, these two guys, Marty Fleischman and Stanley Pons, had a press conference in Utah at University of Utah, and they claimed that they had figured out cold fusion. Fusion is the process that the sun uses to create energy. You take hydrogen isotopes and you put them together and you make helium and a great deal of energy, obviously, since the sun powers our entire planet. So the idea that we could do this cold, meaning there's a way we could do it where right now when we try to do hot fusion like the sun, it kind of melts the apparatus. The reactor has to shut down because it gets so hot. So we haven't figured out a way to contain all of that heat. Basically what we're trying to do is make a mini sun on Earth. And the reason we'd want to do that is because the byproduct of the reaction is helium. Like when you think about a nuclear reactor, you don't think about taking the byproducts of the nuclear reaction and putting them in kids' balloons for birthday parties. But with fusion, that is what you do. You could take the helium and just put it in balloons. So the idea that they had figured out a way to do it in cold manner, meaning a way where the apparatus doesn't melt, was huge. They announced this in March of '89. They published their work in newspapers and magazines. That's not how this works. They were wrong. There were some pretty horrible things said about them after the fact, but in fact, most of them are true about them being incompetent and whatnot. They literally couldn't do the math and didn't understand what it was they were looking at. But they were so excited about this that they needed to tell everybody right away. And so they got their initial data, which again was wrong, and then they told everyone we'd figure this out. And the reasoning behind that was they had heard that a group at Texas A&M and another group in the country of India had been working on this, and they were close to solving cold fusion. So they got worried that they were going to be, the second winner at the Kentucky Derby. Second place doesn't win anything in science. You have to be the first person to announce your findings. So they were worried they were going to get scooped. So basically this was about pride and money led them to do this. So instead of doing what they were supposed to do, which was take all of their data and send it to a peer-reviewed journal. And the way that process works is you take your data that you took from the scientific method. So step 5, you send it to a magazine that produces science stuff. The editor reads it and goes, this seems plausible, or doesn't seem plausible. If it doesn't seem plausible, they send it back and say, give me something better. If it seems plausible, then they'll take it and they'll scrub your name off of it and they'll send it out to several people in your field and say, does this seem plausible? And if it does seem plausible, those people come back and say, yeah, that seems plausible, and they'll publish it. And once that happens, then everybody in that field will try to reproduce what you did. So what was happening here is they put some images and diagrams in newspapers and magazines, and the rest of the nuclear physics world went crazy and they tried to reproduce that and they couldn't. All the different groups, whether they were in the United States, Japan, China, Europe, they could not reproduce their work. And when they finally did get their data, they realized that, oh my goodness, these guys can't do math and they don't understand what it is that they're looking at. So the reason that science works is you need to be able to reproduce everything that you did. So earlier during the syllabus discussion, we talked about being able to communicate. And if you can't communicate well, then what you did doesn't count. So these guys didn't communicate well, and it didn't work because they didn't go through the proper channels. So you communicate with the scientific community and then they come back and verify your results. That's how it works. That's why science is science, because you do something and then you have the rest of the science people on the planet check your work. And again, that's how science works. So that's the scientific method. That's all I have for this video. Nice, short, sweet one.